Hi everybody, this is our first video on thermochemistry. It's chapter 17 in our textbook. We're looking this time at section 1, which is the flow of energy, and it's about heat and work. We'll look at 3 different videos. This is just the first section. Remember that you can pause the video as often as you need in order to take notes. I would recommend trying to draw pictures that I'm showing you. If you can't draw a cup of coffee, then you could just draw a circle and label it as a cup of coffee. But drawing the images should help you. Pause, rewind, you can fast forward as many times as you need to. If you have questions, you can always ask. First thing we're going to do is look at a bunch of definitions here. We have thermochemistry, which is the study of energy changes in reactions and phase changes. We just finished talking about the phase changes, about freezing, melting, sublimation, deposition, and vaporization and condensation. And we're going to look more closely at those in this chapter, specifically about the energy changes that are taking place. One of the things that you need to know is the definition of chemical potential energy. And what that is energy stored in chemical bonds. Like when we eat food, your body breaks down the bonds that are in those things that you eat and gets energy from it. And then heat, which is energy that transfers from one object to another because of temperature difference. We're going to represent it with this little lowercase q right here. It's what our reference table uses, but sometimes you can see a capital Q. Don't ask me why, I have no idea. It always moves from warmer to cooler. I have underneath this, always moves from high to low. The thing to remember is that heat goes with the flow from high to low. You can use that to help yourself on tests. And here's some examples of that. Right here we have a cup of coffee. And if this cup of coffee is sitting on your table, then the coffee should be hotter than the surrounding air that's around it. So in other words, this would be hotter, around here would be colder, and if heat goes with the flow from high to low, it's high here and it's low outside. Now it doesn't just come up out of the coffee, like it's actually going to go into the glass or the mug itself and then out to the air. It would go down and leave a warm spot on the table where it's sitting, but it's going to be coming out of everywhere, from the coffee to the room and to the surroundings. In contrast to that, here is a soft drink, like a cold soda. If it was sitting on your tabletop, then it's going to be colder than your room. And if heat goes with the flow from high to low, it's high out here, so the heat would be moving into your soda. And, you can prove both of these things by knowing that if you left a soda sitting out on your countertop, it warms up. It becomes room temperature. And if you leave the cup of coffee out, then it gets cold because it's losing its heat, and this warms up because it's gaining it. Here's another example that's commonly misconstrued at home. You have a refrigerator, and you oftentimes hear people say, "Close the fridge. You're letting the cold air out," and that's not true because cold doesn't move. That's heat moves from high to low. So it's colder in the fridge and warmer outside. You're actually letting the heat from the room come into your fridge, which is heating it up, and you don't want that. It's going to make your fridge work extra hard. Now, another example that you might see in test type situations to test whether or not you know this idea is an example of, like what would happen if you had, like what happens to the temperature of equal amounts of water at different temperatures. That should be at if they're mixed together. So if you have like this beaker right here with 50 degrees Celsius water and this beaker with 30 degrees Celsius water, if you mix them together, what's going to happen is that they'll come to a common temperature. They'll actually, with equal amounts, they'll meet halfway. They'll be 40 degrees Celsius. Another thing that you could do is if somebody has like an object and this object gets put down into the water, let's say the object is actually 50 degrees Celsius. If you put a 50 degrees Celsius object down here in the water, what should happen is, sort of the same idea. You're not going to be able to predict the temperature exactly until we know a little bit more, but you know that the heat would be moving out of the object and into the water. So the object should cool off and the water should heat up. If you put a 50 degrees Celsius object down inside of this one, then what's going to happen is that there's just going to be equal heat flow. Like there's really going to be no net movement because they're basically the same temperature. Here's some other words that we have. We're going to use them in just a minute. You have system, which is the part of the universe that you're paying attention to. I'll show you in just a second. We've got surroundings. That's everything else. You have the law of conservation of energy, which is a lot like our law of conservation of matter. It says that energy can neither be created nor destroyed. It says in any chemical or physical process. So no matter what you're doing, you cannot create or destroy energy. Now, this isn't exactly true when we get to nuclear chemistry, but that's a conversation for a later day. So I'm admitting right now that there are some exceptions to this, of course. And then you have endothermic and exothermic. Anytime you see endo, we just did these words in the last chapter. Endo means in, exo means out, therm refers to heat. So if you have an endothermic process, you have basically heat going in. I said one that absorbs heat from the surroundings. So the system gains heat and the surroundings cool down. Exothermic means heat go out, so it releases heat to the surroundings. The system will lose the heat as the surroundings heat it up. Now, the whole system surrounding things should get better with some examples. This right here is our cup of coffee from before. If we're looking at whether or not the coffee itself is gaining or losing heat, then that makes the coffee our system, if I can write with the mouse. So the coffee is the system. That means that everything else around it is going to be the surroundings. So that's why we said that the coffee would lose heat to the surroundings. So the system would be cooling down where the surroundings would be warming up. Same thing with the soda. If you have the soda is the system in question. It's what we're concerned with. You could even look specifically at the ice cubes that are in the soda. But right now, just the soda and the ice together make a system. The system is going to be warming up because the heat is moving into it. Now, we can label this as system 2. So if we do this one would be exothermic because heat is going out of the system, and this one would be endothermic because heat is going into the system. And everything, you have to have a system and a surroundings together. You can't have one without the other. And with that, one of the two has to be gaining heat and the other one has to be losing heat. Okay, we have 2 more words. We have calories and joule. Calorie is the heat needed to raise the temperature of a gram of pure water 1 degree Celsius. Yes, someone has actually calculated how much a calorie is. Note to self, if you see a capital C, that is equal, there should be 2 lines there. Sorry, you hear my dog shaking off. That should be equal to 1,000 little calories. So actually, this is meant to be a little c. We could talk a little bit more about this in class. Joule is another unit of heat. I put the actual definition on here, but you don't need to memorize the whole definition. You just need to know that a joule is another way that you can actually measure heat flow. We have heat capacity and specific heat. Heat capacity is the amount of heat needed to increase the temperature of an object 1 degree Celsius. So it's however much heat you need to raise the temperature up of something by 1 degree. You have experience with this. You should know that different things have different heat capacities. For example, if you have dirt outside versus asphalt, dirt doesn't get anywhere near as hot as asphalt does because the asphalt is much more easily raised with sunshine hitting on it. The temperature goes up really quick. It depends on mass and chemical composition. Specific heat is the amount of heat needed to raise the temperature of a gram of a substance by 1 degree Celsius. And these 2 definitions seem a whole lot alike. Here's the thing that makes them different. For heat capacity, it doesn't specify how much of the object, and specific heat does. Liquid water has a very high specific heat. It takes a whole lot of energy to heat up water, and the phase of water determines the specific heat. It is different. We need to look at this in class just a little bit. And metals have a very low specific heat. They heat up very, very easily. We're going to do some work with this in class. You can go ahead and write down the formula. It's Q is equal to MC delta T. And so you can just go ahead and record what those things mean, and then we're going to do a whole bunch of math problems with this once you get to class. And that's the end of that section, so I'll leave it there till the next video.